Hello guys, good morning. In the previous module, we learnt about what is complex variables, properties of complex variables, CR equations with respect to Cartesian and polar forms, and few application problems related to complex variable and complex differentiation. So in this lecture, I'm going to brief about complex line integrals, definition of complex integration and properties of complex line integrals and few examples related to complex line integrals. So already we know the complex variable is a function which contains complex number and it is denoted by f of z is equal to u plus iv, where u stands for real part of the complex number and v stands for the real part of the complex number. So now we will see what is meant by complex integration. So complex integration is an integration of complex valued function defined along a curve in a complex plane. So here the curve is defining in the complex plane and I'm going to integrate that complex valued function along that particular curve is nothing but a complex integration. So now let me see what is meant by complex line integral. So complex line integral is nothing. It is the integral can be evaluated on a particular curve. For example, consider a continuous function f of z of the complex variable z is equal to x plus iy. It is defined at all the points of the curve C. And already I told that the curve is defined in the complex plane here. So now I'm going to extend this particular curve from P to Q and dividing the curve C into n parts. So like I'm taking a curve C having n points P and Q in the xy plane, and we can define this xy plane is a complex plane as x plus iy plane. So now I'm going to divide the curve PQ into n parts like P naught of Z naught, P1 of Z1, P2 of Z2, Pk minus 1 of Zk minus 1, Pk Zk, etc. etc. Pn of Zn. So if we integrate the curve function along with this curve is nothing but a line integral. Usually the line integral is denoted by the equation integration f of z dz over the curve C, where the curve C is defined in the complex plane Z. And here the function f of z is a complex variable and it is denoted by f of z is equal to u plus iv, and dz is nothing but dx plus I dy, where it is defined by a complex number z is equal to x plus iy. So we will get a dz is equal to dx plus I dy. So it is clear that it is defined in the Cartesian form. So to get a polar form of the dz, I'm going to replace x is equal to r cos theta and y is equal to r sin theta, and we can obtain the equation for dz also in polar form. So now we will see few properties related to the complex line integral. The first property is if minus c denotes the curve traversed from Q to P. So actually the curve C will be moving from P to Q in positive direction, but here the curve is moving from Q to P, so I'm taking the curve like minus C. So then the integral evaluated like integration over the region minus C f of z dz is equal to integration minus of the actual integration region, that is minus of integration over the region C f of dz. So next, if C is split into number of parts, so for example the curve C can be will contain infinitely many curves in it. So I'm going to divide that curve C into infinitely many curves like C1, C2, C3, etc. etc. So the particular curve C can be evaluated like this now. So the integral over the region C f of z dz can be written like for each curve, like integration over the region C1 f of z dz, integration over the region C2 f of z dz, plus integration over the region C3 f of z dz, and so on till infinity. Third property is also called as an linearity property of complex integration, and it is given by if a and b are constants, then integration over the region C a f1 of z plus b f2 of z dz can be written as, by taking the constant outside, integrating the functions. So we'll get like a into integration over the region C f1 of z dz plus b into integration over the region C plus into f2 of z dz. So now we'll see one example related to line integral. The problem is like this. Evaluate integration 0 to 2 plus I conjugate of z whole square dz. Along first one, the line x is equal to 2y. Second one, the real axis up to 2 and then vertically to 2 plus I. So here the first thing is we have to identify few things. Conjugate of z stands for x minus iy. So actually the complex number z is given by x plus iy. So complex conjugate z bar will be x minus iy. So the function is here x minus iy whole square. On expanding the equation, we'll get x square plus y square minus 2iy will get it. So dz is nothing but dx plus I dy, and in the first case we have to take the line x is equal to 2y. So we'll see how to expand the first line equation x is equal to 2y. So first, so let me take the curve x is equal to 2y. I'm going to differentiate. It means that in the problem I'm converting all the x variable in terms of 2y. So if x is, I'm converting in terms of y, obviously I should convert dx also. So I'm going to differentiate both sides. I will get dx is equal to 2 dy. So since in the problem z varies from 0 to 2 plus I, it is nothing but the z varies from 0 plus I0 to 2 plus I. So here 2 plus I stands for x plus iy form. So if 2 plus I is x plus iy form, I can expand the limits for x and y like this. So x comma y varies from 0 comma 0 to 2 comma 1 according to the complex number formula x plus iy. So now I am going to replace all these values in the main equation. Therefore integration 0 to 2 plus I conjugate of z whole square dz will be equal to integration 0 to 2 plus I x square minus y square minus I times of 2xy, or expanding x minus iy whole square will get this equation, and dz is nothing but dx plus I dy. So that on replacing x is equal to 2y, since I am converting all the x variable in terms of y variable, so we have to take only y limits here. So I am taking only y limits which varies from 0 to 1. Along with replacing x is equal to 2y, I got the equation like 2y whole square minus y square minus I times of 2 into 2y into y, and dx is nothing but 2 dy again. So 2 dy plus I dy. So take all the common factors. So from the entire equation I'll get the integration y from 0 to 1 3y square minus I times of 4y square, plus here if I take dy common factor I will get 2 plus I into dy. So next, on taking y common factor, I will get the integration y from 0 to 1 3 minus 4i y square plus into 2 plus I dy. So since here 3 minus 4i 2 plus I constant, I can take outside, integrating only y square dy with the limit 0 to 1. So on expanding 3 minus 4i into 2 plus I will get the equation like 6 plus 3i minus 8i plus 4. On integrating y square we will get it y cube by 3 with the limit 0 to 1. So on simplifying the above equation I will get 10 minus 5i. So applying the limit for y cube by 3 I will get 1 by 3. So the required solution is y by 3 2 minus I for the curve x is equal to 2y for the function conjugate of z whole square. The next equation is real axis. So real axis in the sense x-axis here. So x-axis in the sense, so in the limit 2 plus I, the x-axis we can take like the limit varies from 2 comma 0. So because in the x-axis y will be 0, I can take the limits like 2 comma 0, and again it is moving vertically to 2 comma 1. So it is moving the vertically to 2 plus I in the sense it is moving to 2 comma 1. So now draw the curve for the set of points. So since the curve C starts from 0 comma 0, again it is moving from real axis, that is 2 comma 0, and again it is moving vertically to 2 comma 1. So I'll get the equation like this. So now the integration over the region C conjugate of z whole square dz. So here the curve C will be divided into two parts. The first part is O to P, the next part is P to Q. So I'm going to divide the curve C like this. Integration O to P mod z square dz plus integration P to Q mod z square dz. So along OP line. So in the along OP line, we can say the common point is y is equal to 0. So y is equal to 0, obviously dy will be 0. So once dy is 0, only dx will be existing. So we have to find only x limit. So in the OP region, x varies from 0 to 0 to 2. Along PQ region. So along PQ region, we can observe that the common point is x is equal to 2. So if x is equal to 2, dx will be 0. So once dx 0, only dy will be existing. So y varies from 0 to 1. So now, on replacing all these points in the curve C, the equation will be like this. So integration 0 to 2 plus I mod, conjugate of z whole square dz is equal to the first integral along OP. X varies from 0 to 2 with x square dx. If I replace y is equal to 0, dy 0, I got this equation. Again, if I replace x is equal to 2, dx 0, I got this equation. 4 minus y square minus 4 iy I dy. So on integrating the first function with respect to x, I'll get x cube by 3 with the limit 0 to 2. On integrating the second equation with respect to y, I'll get the equation like, I can take I common factor 4y minus y cube by 3 minus I times of 4y square by 2 with the limit 0 to 1. On applying the limit, we'll get 8 by 3 plus I times of 4 minus 1 by 3 minus 2i. On expanding the equation, we'll get the solution like 14 by 3 plus 11 by 3i. So this is a required solution for the given plane. So in the next lecture, I'm going to discuss about Cauchy's theorem and their consequences. Thank you.